In today's lesson, we are going to be looking at arc length and sector area. So this is the second half of, or the part two of our lessons on circle geometry. So in the previous one, we looked at angles and circles, and this one we're going to be looking at some measurements, and specifically arc length and sector area. So we talked about what an arc was in the previous lesson. It was basically a portion of the edge of the circle joining 2 points from two radii or from two radiuses. And the sector area was the area contained between two of those radiuses. So we do have two formulas. One is going to look at what we call arc length. And this is going to help us figure out the distance from one point to another around the edge of a circle. And this formula, say S for the length, is equal to theta times pi times r, all divided by 180. And you kind of can see the components of the formula kind of come from the circumference formula, and then kind of just as a portion or as a fraction of a circle based on the degrees that form the arc. And then for sector area, we have A is equal to pi times or theta times pi r squared divided by 360. So here we can see again the relationship to the area of a circle, because we have the area of the circle multiplied by whatever fraction or portion our sector or our piece of the circle is. So let's go through and use those formulas to do some calculations. So for the first one, we want to calculate the length of the arc AB. So the arc is this whole portion here. So that whole portion is what we're going to be looking at. We want to figure out what is that length. So that's where we use the arc length formula. So S is going to equal theta, which is our angle, times pi times r divided by 180. So theta is 123 times pi times r, which is 6, divided by 180. We go through, we get a final answer of 12.87 centimeters. Right, so this just becomes a calculation, and then we can calculate, just a calculation, we get 12.87. For the next one, the diameter is 24 centimeters, and we want to calculate the length of the arc CD. So again, we're going to calculate this length. If we know that the full diameter is 24 centimeters, then the radius, or just a portion of it, would be half of that, or 12. So we're using a little bit of our knowledge of a circle to determine the radius. Now I can use it in my formula. So I'm not going to keep on rewriting the formula because we've already have one example, but it would be 60 times pi times 12 divided by 180. S is equal to, then when we calculate that, we get 4 pi, or we can say 12.56. So you might see some answers that basically do all the calculations with the numbers. So in this case, 60 times 12, then divided by 18 to get 4, and we leave pi as it is. So we don't really multiply pi through, and that is just because pi is one of those irrational numbers. It's never ending, so we would have to round our values. So we could argue that this is our exact value, right? Similar to when we talked about dealing with trig and with triangles, leaving the answer in with the square root rather than actually solving that to keep it as the exact value. So similar idea. Next one, determine the length of the arc EF, or if we know this length is 5 pi, and we have our arc, or the measure of the arc, we want to figure out what is the length of the radius. So here we're going to use our formula again. So I'll rewrite out this formula just because we're going to be using it a little bit differently. So pi, or theta times pi times r divided by 180. We know the length of the arc, so we know s is going to be 5 pi. So I can replace that with 5 pi. I know I have 30 for my angle. I have pi. I don't know what r is, and I have 180, or divided by 180. So I can go through now, and I can move I'm basically going to rearrange this formula to solve for r. So I'm going to move the 180 up and multiply it with 5 pi. And I'm only going to multiply just the numbers right now. So 180 times 5, we have 900 equals, 900 pi, because pi is still there. 900 pi equals 30 pi r. Now I'm going to divide both sides by 30 pi. This way it does make it a little bit easier because pi and pi will just cancel out. So we get 900 divided by 30, and we get, which is equal to 30. So r equals 30. So that is my radius. So again, we might see some answers or some of the lengths or the areas with pi in it because we're given the exact value. So we can kind of treat it just as some like a variable that we can kind of carry around. We tend to end up dividing it out anyways when we're calculating for other measures. And then the last one, calculate the measure of the length of xy. So again, so s equals the angle, so 70 times pi times the radius, which is 10, divided by 180. We get 700. 70 times 10 is 700, but divided them by 180. So this one doesn't really give us a nice value, so I'm just going to go through and calculate the full thing. So 70 times pi times 10 divided by 180. So some calculators might give you something like this, right, because they want to give you the exact value. That's a little bit messy, so I'd rather just keep it as the decimal. So s would equal 12.21. And that is the length from x to y. So those looking at some of the arc length formulas, we're going to continue through and look at some of these other ones. So again, these are going to go through and still look at the same thing. So I'm going to leave these two for you to try on your own, and then we'll come back with an answer, and then we'll move into some of the sector area questions. So we have two here, a little bit different. We're given the information and we just have to plug it into the formula to try to solve for what is missing. So again, I pause the video and try to work through these two examples. So coming back to the two answers, this is what we should have. Just zoom in there a bit. So look at the first one first. So one, a circle has an arc of length, or an arc of 75 degrees and a length of 88 pi centimeters. What is the diameter of the circle? So I've just drawn a quick sketch over here just to help us visualize it. So I have my circle, I have my arc of 75 degrees, and I have the length indicated. So I'm going to be using the arc length formula, S equals theta pi r divided by 180. I'm going to plug in the information I know. I know the length, or S, is 88 pi. I know theta is 75. I don't know what r is. So now I'm going to solve or rearrange my equation for r. I'm going to move the 180 up and multiply with the 88. I'm leaving pi as is. I'm not going to incorporate it because I don't want to make the numbers too messy and round it too much. So 188 times 88 gives me 15,840. Pi is still there, and then that equals the 75 pi r. To get r by itself, I'm going to divide by 75 pi on both sides, and I end up with 211.2 is equal to r. So that's my radius for this arc length, um, or this sector. But I want to find the diameter of the circle. So then I'm going to basically multiply the radius by 2 and get the diameter, which is 422.4 centimeters as the diameter of the circle. For 2, it's something similar to what we did. We had to use the formula, plug in the information that's given, and then rearrange and solve for the missing piece. So in this case, again, I still drew a sketch. I know the arc length is 14 pi centimeters and the radius is 5 inches. So I needed to convert from inches to centimeters. So going back to the first lesson of the geometry unit, so 5 inches equals 12.7 centimeters. So I included that in my diagram. I then took the formula, S equals theta pi r divided by 180, plugged in the information of the length and the radius, and then I had to solve for theta. Oops. So I did that by, again, bringing the 180 up and multiplying, and got 2,520 pi. So again, I just did 14 times 180. Then I divided both sides by 12.7 pi because I had to get rid of it, cancel it on one side, and then theta would be on its own. Divide by 12.7 on the other side, the pi's just cancel out, and I can do 2,520 divided by 12.7, which gave me an angle or an arc of 19.8 degrees. So again, that's kind of why we use some of the questions just leave pi as is, because it's easier to work with, and it does help the numbers become a little bit more manageable, and there's less rounding error, so to speak. So the next couple of questions are going to be looking at the sector area, or the sector area formula. So in the first one, the area of the circle is 225 square inches. We want to calculate the area of the sector whose central angle is 45 degrees. So I'm going to draw out roughly my circle. I'm going to draw out a sector. Whose 45 degrees is that central area. And I want to figure out what is this area. When I know the entire area of the circle, so this entire thing, that entire area is 225 pi inches squared. So I know the entire area of the circle, and I want to figure out just what is that portion. So that's, even though it doesn't seem like I'm given enough information, I am, because my sector area formula is theta times pi r squared divided by 360. And this portion right here, pi r squared, that's the area of a circle. So if I'm given the area of a circle, I can just plug that in for the entire pi r squared portion. So A will equal theta, or which is 45, times 225 pi divided by 360. So in this one, we could go through and work through it without incorporating pi. So for example, A would equal, if we do 45 times 225, we get 10,125 pi divided by 360. If I were to just work with the numbers, it doesn't work out to anything nice. So I'm going to go through and just continue to solve to get an actual answer. So when I do 10,125 times pi divided by 360, so 45 times 225 times pi divided by 360, I get 88.4 inches squared. So here I can't really rewrite my final answer. I could write it as a fraction with pi to make it the exact value, but it's a little bit messy. So in this case, the numbers don't really lend itself too nicely to having it as an exact value. So I have an approximation, so to speak. And again, either way is fine when you go through and calculate it, as long as you're aware that's why some of the answers are left with pi, like we mentioned before. So for the central angle, again, so this is something similar. So the central angle is 60 degrees. So again, I'm just roughly sketching it so we have an understanding of what it is. We're looking for this measurement, this area. We know the area of the entire circle is 144 pi. So I can go through now and plug it into my formula. Pi r squared divided by 360. Again, like we mentioned, the pi r squared is the area of the circle. So I can just replace pi r squared with the 144 pi. Theta is 60 from our question, divided by 360. Here, if I work through with the values, I can do 60 times 144 and get 8,640 pi, all divided by 360. And when I divide just the numbers, I get a nice value. So I get A equals 24 pi. So this one works out so I get a nice value. If we want the approximation, I can actually then multiply 24 times pi and get a value of 75.4. And this would be, we don't have any units, but units squared. So again, either way, if you get nice values when you're trying to simplify, just focusing on the values without incorporating pi, feel free to use that. Or if it's just easier to go through and do the full calculations, you can do that as well. Next one, circle has a radius of 12 centimeters. Calculate the area of the sector whose central angle is 120. This one is, again, more or less straightforward. We're going all the way kind of back to the original. So 120. And we have a radius of 12. So this one, we're not given the area, we're just given the radius, and we have to go through and find the area of just the sector. So here we're just standard plugging everything in that we know. Again, the formula, theta pi r squared divided by 360. Theta is 120 times pi times r squared, or 12 squared, divided by 360. This one again, so if I did 120 times 12 squared, I get 17,280 pi divided by 360. And if I just were to keep my values, or just focus on the values, 17,280 divided by 360 is 48. The pi gets carried through. So I could have an exact value of this, or I could go through and calculate what the exact value, 48 times pi, and we get 150.8 centimeters squared. So in either way you choose to do it is up to you, whatever you feel comfortable with. 6, the central angle is 72 degrees and the sector has an area of 5 pi. So again, this is something similar to what we've done before. Same with 7, calculate the measure of the central angle. So this one, actually 7 is a little different, but I want you to try to go through these two. They're not unlike things that we've done with the arc length, especially for 7. 6, we have done things before. So try to go through these two before we move into some additional or other problems that we might encounter with circles. So try to practice the sector area formula on these two questions. So recommend pause the video and try to work through these two questions. So coming back to these two answers, they are actually, apologize because I was looking at the one when going through it. We haven't done too much of this with sector area. We have done stuff like this with the arc length formula. So the process should be relatively familiar, just with a different formula. So for 6, we were given the measure of the central angle, and we were told what the sector area was. We wanted to calculate the radius. So we start with our area formula, we plug in the information we know, and then we go about rearranging and solving for r. So here, what I did was I multiplied 5 by 360. Again, similar to when we did arc length, I'm leaving pi as much as possible alone. So 5 times 360 is 1800 or 1800, which left me with 72 pi r squared. I divided both sides by 72 pi, which would then cancel the pi's out and allow me to have 25 equal to r squared. Then to find r, I square rooted both sides and got 5. So again, it's all just rearranging the calculation and the equation and solving. For 7, I was given the area as 20, or the sector as 20 pi. I was told the radius, and we needed to figure out what the central angle was. So similar idea, start with our formula, plug in the information we know, and solve for our unknown. In this case, the unknown was theta. So I started by multiplying both sides by 360, or by multiplying the one side by 360. Actually, there should be a pi there. So 20 times 360 is 7,200. Again, I'm leaving pi. Forgot to kind of write pi in there when I was doing it. But I'm leaving pi for now. And on the other side, I can simplify the 6 squared, which gave me 36. I then went through and said, okay, well, I need to get theta by itself, so I need to divide both sides by 36 pi. Divide the other side by 36 pi. The two numbers divide to 200. The pi's cancel out, so that means theta equals 200. So again, it's just the idea of plugging values in, rearranging the equation, and solving to find the missing piece. So some other problems that we might come across. So for example, a sector area is shown. Determine the maximum width of the sector, the distance from A to C. So in this one might be a little bit different because we haven't talked about this too much, but this is going to incorporate some of the other stuff that we've looked at. If I know that both of these are radiuses, they're equal. And if I was to form a triangle, right, these two angles would have to be equal. I know one angle is already 68, so then these two angles we'll call x. So x has to equal, 2x has to equal 180 minus 68, or 2x has to equal 112, or one angle has to equal 56. So I now know that each of these angles is going to be 56. Because these two sides are the same, it's an isosceles triangle, so those two angles have to be the same. Now, do I have enough information to find this unknown side of AC? Or you could say little b. And in this case, we do. Right? This is a triangle. It's not a right angle triangle, so we can use our sine law because we do have a full pair and half a pair. So again, thought we were away from trig, but not really. Right? I'll use a different. We have a full pair. We have half a pair and a full pair. So sine of sine 68 over b is equal to sine 56 over 12. We can go through and solve for the unknown. So we get cross multiply first. So 12 sine 68 equals b sine 56. Move the sine 56 over. We get 12 sine 68 divided by sine 56 equals b. This just becomes a calculation, and we get that length between A and C is going to be 13.42 centimeters. So combining trig with a little bit of our circle geometry to find lengths. The next two. One, a glass shop needs to cut a circular piece of glass to match the shape below, and we want to calculate the diameter. So if we have 45, 45 is the length here. We can say that somewhere along this dotted line is our center, right? Doesn't really matter where it is right now, but then I can say, well, the radius is going to connect those two parts. So if I have my radius connecting both two parts, these two sides are the same. So this one might be a little different. This one might be involving some theorems that we haven't quite looked at yet. Because when I went through and I did it, I made an assumption that I was at a 90-degree angle, but we don't know that for sure. So I apologize if this is kind of like cuts abruptly, but I had to do a little bit of searching. It's a problem when you kind of come up with questions, or you find questions and you think they apply. So this one is a little bit different, but this does involve, again, similar to the last lesson where there was kind of like a theorem that we didn't really talk about too much. There is a theorem in circles that talks about chords and how they intersect. So we are assuming that this is going to be the portion of our diameter, and we can clearly see that a portion is cut off because the diameter bisects or intersects with my chord. I can say that it intersects it at 90 degrees. So in this case, and it would split it in half, so each side is 17.5, 17.5. So the theorem states that the product of the two portions of a chord, or the two lengths of a chord that intersect, are equal. So in this case, 17.5 times 17.5 is going to equal 45 times something. We'll call it A. And A is going to be this little portion here. So by going through and doing that, I can figure out what the additional portion is and then figure out the diameter by just adding it to 45. So in this case, we get 17.5 times 17.5 divided by 45, which will equal A. 17.5 squared divided by 45 gives us an A value of 6.8 for A. Therefore, the diameter is equal to 45 plus 6.8, or 51.8. There are other ways we could have done it if we were given a little bit more information, right? If we were given where the or the distance from the chord to the center, then we could use trig to solve that. However, or if we made assumptions that when the radius meets, basically if we were forming kind of like the arc length, then we would have two. If we knew that it formed a right angle triangle, then we could make some assumptions there. But with kind of the lack of information, it was a little bit harder to do that. So we're going to go with this one. And there may be other ways to do it as well. There might be something I'm missing. C, so this one is similar. Now we're given a little bit more information. We're told that from the top of the circle to the center has a diameter of 80, and the length of this segment is 60, and we want to cut off this portion. So we need to figure out, okay, how far in do we have to cut? So in this case, we are given a bit more information, and especially that the diameter is 80. So here, if the diameter is 80, then I can say that halfway, right, from my, at my center, or the center of my circle, to one end, I know that would have to have an angle or a measure of 40, because it's a radius. Same with the other one. I know that would have to have a measure of 40 as well. So I know that these two measurements have to be true because they're both radiuses, so we can make that assumption. And I can also assume that the diameter is going to intersect the chord at 90 degrees, bisecting it to make each segment 30. So what I can do now I can figure out what is this height. I can figure out what is this height here because I have a right angle triangle. Right, so if I were to just draw that separately, I have 30 and 40, and I'm looking for this height. Because once I know that height, I can subtract it from 40 to figure out this missing piece. Because I know that from the center to the edge of the circle should be 40. And if I know what that piece is, then I can figure out what's missing. So this is just going to be Pythagorean theorem. Because we're looking for a leg, x squared equals the hypotenuse squared minus the other leg squared. X squared equals 720, x equals 26.5. So that means that this measure is 26.5. So that means the remaining measure, other side, 26.5, has to be 40 minus, we'll call this b. Say b has to equal 40 minus 26.5. B equals 13.5 centimeters. So that means we have to basically cut in 13.5 centimeters from the top. Actually, going back, there was a slight error, slight calculation error. So it should be the square root of 700. Give me 26 point. That still gives me the same value, 26.45, rounded up to 5. So it doesn't change it too much, just for clarity. It should be the square root of 700. So again, the main thing from this, though, there are some additional problems here that we just kind of looked at the end. The main thing, though, is looking at these ones, the sector area and the arc length. So those are the main things that we should be looking at, or the main takeaways I want you to understand. The other ones are just additional extension kind of types of questions. These two are the main ones, are the main formulas that you should be